There are many approaches for solving differential equations numerically. In this video, I'll introduce what is probably the simplest approach. In spite of its simplicity, it was the approach that I used about 90% of the time when I was in industry and needed to solve differential equations governing rocket engines. The approach is called Eulers Method, and it simply involves substituting the approximation to a derivative from chapter 15 into the derivatives present in our differential equations. Derivatives are defined by calculating the slope of a line from 2 points that are infinitesimally close together. Numerically, we can't let delta x be 0. For our numerical approximation of derivatives, we just chose a small delta x and hoped that the approximation was good enough. Then we checked whether the approximation was good enough by reducing delta x until the solution converged to some consistent value. A similar approach can be used to solve differential equations by just substituting this formula in for the derivatives in our differential equations. Then we can solve for the value of the function at the position x plus delta x. I'll illustrate how this is done with the examples I used in the previous video on writing differential equations. The first example will be a problem that we solved in chapter 16 when I introduced integrals. The system is a mass on frictionless rollers that's subjected to a force. This is the differential equation that describes the system. The derivative is the mass's velocity with respect to time. Our goal is to solve for the velocity itself as a function of time. Keep in mind that in chapter 16 we needed an initial velocity of the mass just before the force was applied. This gave us our constant of integration, which is called the initial condition when solving differential equations. If we substitute the approximation to a derivative from the previous slide for dv dt, we get this expression. We get to choose the value of delta t, which is commonly called the step size or the time step. The equation can be rearranged to solve for the velocity at a time t plus delta t if we know the velocity at time t and the slope of the velocity curve, f over m. The process of solving the differential equation is actually an integration. This is the equation we're using to solve the differential equation. We also need an initial condition, which is that the velocity of the mass at time t equals 0 is 0. We're going to solve this for the case of a constant force, just as we did in chapter 16. The acceleration is the ratio of the force to the mass, so acceleration is just f over m. Notice that this is also the slope we use in our equation. The velocity curve will be shown here. At the moment, all we know is that the initial velocity is 0. So in our equation, t is equal to 0. The ratio of the force to the mass at time 0 is just the acceleration at time t equals 0. This term here is then just the area under the acceleration curve between 0 and delta t. So the velocity at time delta t will be the acceleration times the delta t plus the initial velocity v equals 0. We're integrating the acceleration curve to get velocity, just as we did in the chapter on numerical integration. Now let's solve the equation if t is delta t. Then our initial condition is the velocity at time delta t, and we'll solve for the velocity at time t plus delta t, which is just 2 delta t. This velocity can be determined by calculating the area under the acceleration curve between delta t and 2 delta t and adding that to the velocity at delta t. So the velocity at 2 delta t is the velocity at delta t plus the area under the acceleration curve. By repeating this process, we can keep working our way along the velocity curve for as long as we want. Now let's generate MATLAB code to perform this process. As usual, I'll write some pseudocode and use that to create a MATLAB program. First, of course, we need to initialize variables. I'm going to store the velocities and times in arrays. The first element in the velocity array will be the initial condition, so v of 1 is 0. Choosing a time step size and an ending time for the simulation will give us the time vector. Finally, we need values for f and m. Now we can calculate velocity values for the remaining elements in the time vector. I'll use a for loop to do this. We have the first element in this array, so we'll start our calculations at k equals 2. For each value of k, the velocity at the kth element will be the velocity at the previous time step, v of k minus 1, plus the slope, f divided by m times the time step, delta t. That's all we need to do, so we can end our for loop. Now I'll implement this algorithm in MATLAB and see how it works. I'll create a script file named firstorder.m inside my current working directory. I start out by initializing variables. I'll choose a time step size arbitrarily as 0.1 seconds and name that dt. My initial condition will be 0 meters per second, and that'll be the first element of my velocity array, v. My time vector will start at 0, end at 3, and the spacing between points will be the time step size, dt. The last things I need to initialize are the force and the mass. I'll set the applied force, F, to be 10 newtons, and the mass to be 1 kilogram. Now I can set up my looping structure. I need to calculate velocities corresponding to the second through the last elements of the time vector. The kth velocity point is equal to the k minus first velocity value plus the force divided by the mass times the change in time, dt. That's all I need inside the loop, so now I can terminate it with an end statement. Last, I'll plot the velocity as a function of time. Now I'll save the file and return to the command window. I'll run the file by typing the name of the file at the command prompt. The velocity is a straight line, which I would expect from a constant force. The slope of the line is 10, since the elapsed time is 3 seconds, and the final velocity is 30 meters per second. Now let's add damping to the example as we did in example 2 of the previous video. This was the equation that governed that system. Again, all we have to do is substitute the approximation to the derivative into this equation and solve for the velocity at time t plus delta t. This is the expression we end up with. Now the velocity at the next time step not only involves the slope at the previous time step, but it also depends on the velocity at the previous time step. This time, rather than doing the process graphically, I'm going to demonstrate the first few calculations. These are the parameters I'm going to use in this example. So the first time step is t equals 0, and my initial condition is v at t equals 0 is 0. Now at the next time step, I increase 0 by delta t. So at time 0.1, the velocity at 0.1 is delta t, which is 0.1 over m, which is 1, times f of t, which is 2, minus b, which is 2, times v of t. I take this and put it in there, plus v of t, which is also 0. This is 2.2. The velocity at time t equals 0.1 is 0.2. Now, 1 delta t later, time is 0.2. This is still delta t over m, which is 0.1 over 1. F of t is constant. It's still 2. This is minus b, which is 2, times now the velocity at the previous time step is 0.2. And then I add the velocity at the previous time step, 0.2 to that. This becomes 0.16 plus 0.2 is 0.36. One more time step later, at 0.3, this will still be 0.1 over 1 times 2 minus 2 times the previous velocity, which is 0.36 plus 0.36. And we can just keep working our way through time that way. Now let's modify our previous m file to calculate the velocity of the mass with damping. The looping structure is the same as before. We only need to change the mathematical expression within the loop to include this v of t term. I'll start with the m file from the previous video. I'll save it as a file named damped firstorder.m. First, I need to define a damping coefficient. I'll set b to 2. Everything else is pretty much the same, except for the equation to evaluate inside the for loop. The equation is now that the velocity at the kth time step is equal to the velocity at the k minus first time step plus the time step divided by the mass times the force minus the damping coefficient times the velocity at the previous time step. I'll save the file, go back to the command window, and run it. This looks pretty reasonable. The mass approaches its final velocity gradually, as we'd expect. The final velocity is where the mass is no longer accelerating, so the damping force and the applied force cancel exactly when the velocity becomes constant. The final velocity is 5 meters per second, and the damping coefficient is 2, so the damping force is 2 times 5, or 10. This is equal and opposite to the applied force, 10 newtons, so that seems reasonable. There are a couple of important issues relative to solving differential equations numerically. The first of these is whether the solution is accurate. We can usually resolve this with the same approach we used for differentiation and integration. In those cases, we reduced the spacing between points until we got a consistent result that was independent of further decreases in spacing. A similar technique is commonly used when solving differential equations. Solve the equations with some arbitrary step size, then reduce the step size and check whether the solution changes significantly. If the change is above some threshold, continue to reduce the step size until the results become independent of the step size. Another issue is stability. An unstable solution will tend to grow until it becomes infinite, as I'll illustrate in my next demonstration. Stability depends on the problem being solved and the solution approach used to solve the problem. Some solutions will become unstable if the step size is larger than a certain upper bound. Some problems will be unstable for certain solution approaches regardless of the step size used. Now let's take a look at our previous example to see the effects of accuracy and stability. Let's reduce the time step size from our previous example and see how that affects the accuracy of the solution. But first, let's calculate the exact solution to the problem and add a plot of that to our figure. The exact solution is y of t is equal to 5 times 1 minus e to the negative 2t. Now I'll hold the figure and add a red dotted line representing the exact solution. Now I'll edit my previous script file. I'll be redefining arrays, so I should probably first clear the old arrays out of the workspace. The first time, I'll cut my step size by a factor of 10. I'll also change my line style. I'll save the file, go back to the command window, and rerun the file. The numerical solution is now closer to the actual solution. I can see that better by zooming in on the two lines. Now let's try reducing the time step by another factor of 10. I'll also change my line style again. I'll use a green line this time. I'll save the file again, go back to the command window, and rerun the file. Now the estimate's even closer to the exact value. I could continue to improve the estimate by reducing the step size again, but I think the point's made. Now let's take a look at the effects of increasing the time step size. First, let's try a time step size of 0.75. I'll also change the ending time to 10 seconds. And I'll plot the result as a solid magenta line. Not only is there a lot of error now, but we're also seeing oscillations in the result that really shouldn't be there. The solution overshoots the final value now, and then tries to overcompensate by undershooting. The oscillations do get smaller as time goes on, and it gets to the correct result as time gets large, but overall the solution is pretty useless. Now let's try a step size of 1.0. I'll use a solid black line to plot these results. Now the oscillations don't even damp out. The solution oscillates between 10 and 0 and back to 10 again. Now let's increase the step size again to 1.25. Now the oscillations get larger as time goes on. If I ran this simulation for long enough, the solution will try to go to infinity and we'll start getting overflow errors. This is an unstable solution. Increasing the time step size even more typically causes the oscillations to grow at a faster rate. So, for Eulers' method anyway, smaller time steps make the solution more accurate, and increasing the time step excessively can result in oscillatory and unstable responses. This is a typical trend, but it's not at all universal. Different solution approaches have different characteristics, but the mathematics associated with describing them is beyond what we want to do in this class. Finally, let's take a look at the third example from the previous lecture, in which we added a spring to the system we used in the previous example. For this example, our model of the system consisted of two differential equations in two unknowns, the mass's velocity and the spring's displacement. We can replace the derivative in the first equation with its approximation to get this equation. Replacing the derivative in the second equation results in this equation. Both of these equations can be rearranged to provide the velocity and the displacement at time t plus delta t in terms of the velocity, displacement, and applied force at time t. The solution approach with two equations is similar to that for one equation. We simply have two equations in our loop rather than one. Let's modify the script file for our previous example to see the effects of the spring. I use the script file from the previous demo as my starting point, but first I'll save it under a new name. I'll change the time step back to 0.1. I also need to set an initial condition on displacement. So x of 1 is equal to 0. For this case, I'm going to change my applied force to 100 newtons, the mass to 5 kilograms, the damping ratio to 5, and I'll add a spring rate of 10. Since I've defined a variable k to be the spring rate, I can't use k as the counter in my for loop. I'll change that to index, and I'll add the spring force to the velocity calculation. I also need to calculate the displacement at the next time step, so I'll set x of index equals x of index minus 1 plus the time step dt times v of index minus 1. Finally, I'll include a plot of the displacement in my figure. I'll use a red dotted line. I'll save the file and then run the new file. This seems to make sense. A spring mass damper system can oscillate, and the final value of both velocity and position makes sense. The final position is 10 meters, which is the same as the applied force divided by the spring rate. So at the final position, the spring force counterbalances the applied force. The final velocity is 0, since with a constant force, the system should come to a rest. That concludes my discussion of the basics of numerical solution of differential equations. There are lots of variations on this, and there are hundreds of textbooks that talk about different approaches to solving differential equations. MATLAB alone has over a dozen commands that will solve differential equations, all of which use methods that are more sophisticated than the Eulers method presented in this video. Eulers method, however, is the simplest and will be sufficient for many engineering problems.